We'll talk about friction, dry friction, lubricated friction, and heterogeneous interfaces. Then we're in the session from the lab to the field. I'd love to tell you about field and real fault, like the Dead Sea fault. However, I'm afraid that it will be more useful for Jay to know whether it's better to ski on banana peels or to do yoga posture on banana peels. No, seriously, I don't know if you realize how much ski is important for science in Jay's lab. At the morning, the first cup of coffee is for talking about the ski conditions in the Alps of next winter. The second cup of coffee is for science fiction until the lunch. And then in the afternoon, we can work, like real science. Then this work has been done here with Ilya and Jay when I was a postdoc here, and I'm now in Lyon. Who wasn't here for the Ilya's talk yesterday? Good. That's good and embarrassing because we have a lot of common slides, but fine. If I do this experiment, I press 2 blocks together, then I'll have, following the classical friction law, I'll have to apply a shear force proportional to the normal force with the proportionality is the static friction of coefficient. And this seems to be a reasonable law when we consider that the real area of contact is much smaller than the nominal one, right? Solid surfaces are rough, and when they are brought together, only the highest asperity from contact. Therefore, the real area of contact is really small. But then, at the onset of sliding, we should detach the surfaces and break the contacts. And this is a quite complex dynamics, and this is too simple law to capture this dynamics. Indeed, at the onset of sliding, we see a rupture propagating along the interface, breaking the contacts. And this is I'll comment the contact area measurement later. Then as you know now, from Ilya's talk, this rupture front is actually a shear crack. But under certain conditions, we also observe ruptures that are arrested at some point along the interface before to reach the other side. And during this talk, we'll define these certain conditions and try to check each of them. Then I'll present first the experiment. We'll talk about detachment fronts both under dry and lubricated conditions, and then we'll see the conditions inducing a rupture arrest. The experiment, this is Ilya's slide. We press 2 blocks together of PMMA, a transparent plastic. Then we send a sheet of light on the bottom block with an incident angle higher than the angle of total internal reflection. It means that if there is no contact, the light is simply reflected. If there is a contact, the light is transmitted through. Therefore, the transmitted intensity is proportional to the real area of contact. And we record this intensity with a fast camera. Then, as you know, we average the intensity measurement over the z direction here. Then we consider the interface as unidimensional. We also measure the 3 components of the 2D strain tensors along the interface, approximately 20 different locations, slightly above the interface, 3 millimeters above. We use strain gauges at a high rate of 1 megahertz. We use dry interface and lubricated interface under boundary lubrication regime. It means that there is only a thin layer of lubricant covering the surfaces. The gaps are not filled here. And our high-tech procedure consists in applying a lot of lubricant, silicone oil or hydrocarbon oil, wipe it, it makes it very thin. This is a typical experiment. Then we apply a normal force, here up to 400 kilograms. Then we shear the system until it enters in a stick-slip regime. We record the contact area measurement preceding each sliding event, then the drop of force. Then here are the measurements. X is along the interface. The y-axis is time in milliseconds. And each line is a snapshot of the real area of contact normalized by the initial one. Then orange color is 1, cold colors are a fraction of 1. And what we see here is a front propagating from the left to the right. Initially, contacts are intact. And as the front passes, the contact area is reduced, meaning that contacts are broken. That's why we say, and important, macroscopic sliding occurs only once the front traverses the entire interface. That's what we say that the detachment of the blocks is mediated by propagating crack-like front, and it's not only crack-like, it's actually true crack. To show that, we compare our strain measurement to the solution given by the linear elastic fracture mechanics, LEFM. Then the LEFM predicts that strain and stress should be singular at the crack tip, the singularity going as 1 over square root of r being the distance from the crack tip. K is the stress intensity factor, or the intensity of the singular field. And then when we compare this solution to our measurement, this is what we get. Here we have the 3 components of the 2D strain tensor as the rupture propagates. The rupture tip is in 0 here. And the black line here is the fit of the LEFM solution. You see that the agreement is excellent. And here there is only one fitting parameter, K. And K is related to the flux of energy, the energy release rate, G, the elastic energy flowing from the bulk to the crack tip. A propagation condition for a crack is that G balances gamma, the fracture energy, or the energy dissipated per unit of advance of the crack. Then actually, by fitting K, we get a measurement of gamma, the interfacial fracture energy. And here for this experiment, gamma is about 1 joule per square meter, which is reasonable value, taking into account the sparseness of the contact. Okay, then what we see here is that the detachment fronts are true shear crack, and that by fitting the strain field measurement, we actually get a measurement of gamma, the interfacial fracture energy. These results are valid for dry friction. What about lubricated friction? Then, under boundary lubrication regime, first of all, we do observe stick slip. Here you have the loading curve for a dry experiment, and here for a lubricated experiment. We see that the lubricant weakens the interface. Friction coefficients, both static and dynamics, are smaller than in the dry case. And we also see that preceding each sliding event, we have a rupture front propagating along the interface, as in the dry case. Is this rupture front a shear crack? Let's compare the strain measurement to the LEFM solution. Excellent. Here for the dry experiment, the one you've seen before, and here for the lubricated experiment. And the black line again is the fit of the LEFM solution. The agreement is as good for the lubricated than for the dry. Then the rupture is a shear crack as well. Nothing changed. But the fracture energy. Here for the dry experiment, I use the fracture energy of 2 joules per square meter to fit the data. For the lubricated experiment, I use 23 joules per square meter, an order of magnitude higher. It means that a lubricated interface is weak in the sense that it reduces the friction coefficients, and is tough in the sense that it increases the fracture energy. And I don't want to talk more about that. We will just use lubrication here. But the reasons we thought about are that it could be that the lubricant layer is actually solidified under the very high pressure at the contact level, and then it enhances the strength of a contact. The other possibility is that there is an elastic coupling between the liquid layer and the solid contact, again, enhancing the strength of the contact. If you want to know more about that, we can just discuss after the talk, or you open this paper here. Then we've seen that the transition from stick to slip is mediated by a rupture front traversing the interface. But I gave you a teaser that we also have arrested rupture. You see here during the loading this tiny drop of force they are actually induced by this kind of partial rupture of the interface, which is arrested before to reach the other side. And actually, there is no macroscopic sliding associated with this rupture, right? The interface is pinned here. And actually, all these tiny drop of force are associated to a partial rupture. And as the loading, then the shear force is increasing, the rupture is longer and longer until it traverses the interface. Why are we interested in such ruptures? Because they are the exact analogs of the earthquakes in the lab, right? An earthquake is a finite size rupture along a fault. It is arrested at some point. And I'll show you that fracture mechanics govern the rupture arrest. What's a crack arrest criterion? A crack arrests when G, the energy release rate, becomes smaller than gamma, the fracture energy. Then in our experiment, we measure the fracture energy by fitting the dynamic strain field. But we can also measure G, or calculate it, from the drop of stress induced by the crack propagation, the rupture propagation. Then G is related to the square of the stress intensity factor. E is the Young modulus. And at the arrest, as the front velocity goes to 0, all the quantities become static, K stat. We can calculate K stat using, for example, the Eshelby formulation by integrating delta sigma, the drop of stress induced by the rupture propagation, divided by the singular field. Then delta sigma is equal to the initial stress before the front passed minus the residual stress, what's left in the wake of the front. Then we see in this criterion that an arrest can be induced or by an increase of gamma along the interface or by a decay of G, the energy release rate. And as G is related to delta sigma, a decay of G can be due to a decrease of the initial stress or an increase of the residual stress. Then now we'll study each of these parameters. Let's start with a decrease of the initial stress. We performed this experiment where we apply the shear at the corner of the bottom block with a point-like pusher. The effect of this loading is actually to concentrate stresses at the corner, and then we have a decay of pre-stress along the interface. And under this condition, we actually get partial rupture during the loading of the system. Then for this event, for example, we also measure the residual stress. Then by subtracting these two curves, we get delta sigma, the drop of stress. Then we integrate it following the Eshelby integral. We get a measurement of G, normalized by gamma, the fracture energy of the interface. And then we determine the location of the arrest by applying the arrest criterion. The rupture should arrest where G becomes equal to gamma, and we compare this location to the measured one on the contact area measurement. Now, if we do that for all the partial ruptures of the experiment and a lot of different experiments, we actually get a good agreement between the predicted length of the rupture by the crack arrest criterion and the measured length of the rupture measured on the contact area, right? This is slope 1. Thank you, Mokhtar. I didn't have time to talk about. No, yeah, actually, we don't really do a prediction. We have to measure the residual stress a posteriori, after the main event propagated along the interface, because we actually can't guess what would be the residual stress. Then we need the interface to be totally broken in order to measure it. And actually, we checked that as the rupture are propagating, the residual stress where it actually broke is always the same. And it seems to be a reasonable assumption to use the one of the main event for the partial ruptures. Okay, then this result is quite important from a lab point of view, it's an additional confirmation of the fracture paradigm for understanding friction. Here, we used an energy balance to define a crack arrest criterion, while we could have never done that using force balance, like friction coefficient. From a field point of view, what we've done here is to predict the length of an earthquake. Remember, an earthquake is a finite size rupture along a fault. Then obviously, on the field, we don't have the drop of stress on the fault directly. We don't have the local fracture energy. But still, we think it's maybe a direction to think about. Yes, a decay of the initial stress induces an arrest. What about an increase of gamma? Remember, we have this great tool of lubrication to increase the fracture energy. Then now what we do is to apply a lubricant under boundary lubrication on only part of the interface. Doing that, we create a step function in fracture energy, right? Now, when a rupture nucleates, if it nucleates in the dry part, it will propagate, and as it encounters the lubricated patch, it actually encounters a jump in fracture energy. And what we observe is that or the rupture propagates in the dry, then in the lubricated part, or it is arrested. And we can even be quantitative about that. Let's apply our criterion. For both event A and B, we'll calculate G. Then for event A, we see that the rupture propagates in the dry part, and as it hits the corner of the lubricated patch, G is approximately equal to gamma lubricated. Then it can propagate further. For event B, it propagates in the dry part, but as it hits the corner of the lubricated patch, G is smaller than gamma lubricated, then it cannot propagate further. And that's neat. And like, if we didn't know about fracture mechanics, this result would be very puzzling, because even though the lubricant reduces stresses, both initial and residual, it induces an arrest of the rupture. But from a fracture mechanics point of view, it's totally straightforward, right? Increase of gamma, you get an arrest. Now, from a field point of view, we're in the session from the lab to the field. What would be actually the effect of a lubricant on the earthquake propagation? Like, can we imagine a patch of melted rock, or like if there is some infiltration of water in rocks, can it arrest a crack? And this I ask, I don't know where they are, Amir, Zeev, I don't know.
Infiltration of water into rock.
Okay, but I don't know if water is a lubricant. But let's say, if we could apply oil, we could arrest a crack, an earthquake. Increase of gamma, yes, fine, we get an arrest. The last one, what about an increase of the residual stress? Then now again, we use the lubricant, but because it will reduce the residual stress. Then in the previous experiment, we applied the patch of lubricant on this side. It was boundary lubrication, and we got the nucleation in the dry part. Now we apply a patch of lubricant on this side, and it's a thick layer in order to enforce nucleation of the front in the lubricated patch. And as I told you, the effect of the lubricant now is to reduce the residual stress. Then as the rupture propagates from the lubricant to the dry part, it actually encounters this barrier of residual stress, this increase in sigma residual. Then again, in this experiment, we observe partial ruptures during the loading. And if we look at this first partial rupture, for example, we measure the initial stress, the red curve here, and we see that initial stress in the lubricated patch, I have the arrow here to show you where it is located, the initial stresses are higher than the residual one. However, in the dry part, they are much lower than the residual stress. Delta sigma becomes significantly negative. And it's the same process for all the partial ruptures of this experiment. You see each time the initial stresses here are higher than the residual, and it's always smaller than the initial stress in the dry part. And actually, calculating delta sigma, we can measuring delta sigma, we can calculate G and get the arrest location as before. Then here, we see that this is this barrier of residual stress that prevent the propagation of the rupture in the dry part. And I just would like to open a parenthesis on the weakening process of a lubricated patch. Because obviously, when I apply a patch of lubricant like that, I reduce mu s, the macroscopic static friction coefficient. And the longer is the patch, the smaller is mu s. This is this plot here. And actually following, this is exactly what is explained by Bowden and Tabors, that mu s should be proportional to mu dry, the friction coefficient of a totally dry interface, and mu lubricated, the one of the totally lubricated interface. But think about it. How does it work? Like, does it mean that the lubricant patch will hold until a force higher than its shear resistance for the dry part to be ready to break? Like, it doesn't make sense. And the answer lies in arrested ruptures. How do we get such a heterogeneous stress profile at the end? By the dynamics of arrested rupture. What happens is that a rupture nucleates in the lubricated patch. As it propagates, it releases the stress up to the residual stress level. But because the initial stress in the dry part are smaller than the residual one, it is arrested. As it arrests, there is a concentration of stress around the rupture tip. It's like the singularity is frozen. Now the next rupture is nucleated. Again, it releases the stress in the lubricated patch. But then now, it can propagate further along the dry interface, both because the shear force has been increased, we loaded the system more, and because of this concentration of stress due to the previous arrest. And it's going like that, pushing the stresses along the dry interface. And that's because of this dynamic of arrested ruptures that we can build this very heterogeneous stress profile. Right? Then it's not that intuitive how you get to the result of Bowden and Tabor if you don't know about partial ruptures. Excellent. Then from our crack arrest criterion, G becomes smaller than gamma. We actually have shown that, yes, with all these conditions, we can get an arrest. And as a conclusion, I would like really that you understand that there is no general case. For each specific experiment, I should take into account all these parameters: initial stress, residual stress, and fracture energy. There is no other way to predict a rupture arrest. And actually, the proper way to do it is to derive the equation of motion of the rupture, as Ilya has shown you yesterday. Right? These are only specific cases of the equation of motion.